going to talk today about energy in electromagnetic radiation. Okay, so last time we saw, well, let's just show it again real quick. The radio transmitter. So the amplitude, or the wavelength of this transmitter is about a decimeter, about 10 centimeters, which translates into the radio frequency. And we bring it near this receiver. Okay, just another wire with a light bulb. The light bulb lights up. And so we can ask the question, well, it lights up, meaning it's dissipating energy, so where's the energy coming from? It's got to be coming from the radiation, right? The radiation is from the antenna is delivering energy to this receiver, and then that energy is being dissipated away. So we're going to talk a bit today about energy in radiation, and particularly about energy stored in fields, because we know there's such a thing as electric potential energy. Okay, we talked about that. But the question is, how is this energy delivered, or where is this energy actually stored? And it's really stored in the field itself, in the electric and magnetic fields. And this is true not just for radiation, but for any electric and magnetic field. And here's an example, which was actually worked out in an earlier chapter, but let's do it now. Let's say you're charging a capacitor. So here's a conventional current. Here's one plate of a capacitor. So this is becoming more positive. This is becoming more negative. And, of course, there's going to be an electric field in here pointing in that direction. And so there's going to be a potential difference across the ends of the capacitor, or across the capacitor plates, right, inside the gap. And we know something about power, right? Electric power. Power is energy per unit time. And what's the formula for power? Electric power in general? IV, I delta V, right? I, the conventional current times the potential difference, okay? So we could work out from the formula for power the amount of energy that gets stored in the capacitor after some amount of time, because power is energy per time, right? So we can say that energy per time, meaning the rate of change of energy, and here I'm using E, let me write it as En. Or let me use a script E here to indicate energy, to distinguish it from electric field, which is going to show up in this equation. So dE dt is I times delta V, and the current is, conventional current is dq dt, right? That's the rate of charge flow, coulombs per second. And so if I want to get the amount of energy, I can integrate through over time, or essentially do the antiderivative here, and just think about the differentials. Essentially, the dt's go away on both sides. And so we have a small amount of energy being equal to a small amount of charge times the delta V. We also know something about the capacitance. And this is something we haven't dealt with for a while. But capacitance, anybody remember the definition of capacitance? The amount, or the strength, the ability of the capacitor to hold charge. Say again? Not 1 over resistance. Has to do with the charge and the potential difference, right? It was defined in terms of the charge and the potential difference. And the capacitance turns out to be Q over delta V, okay? So that's a formula from a while back that you might not remember, but capacitance, capital C, is Q over delta V. So I can put the charge, or I can put delta V actually, in terms of the charge and the capacitance. So I can say delta V across the capacitor is equal to the charge on one of the plates. Okay, so this charge is, if this is plus Q, then this is minus Q. It's the charge on one plate, okay, or one side of the capacitor. Plug this in, I have The change in energy is equal to a change in charge times charge over capacitance. And this is an equation we could solve. This is because we can just do the integral of both sides now. We can say that the amount of energy stored is the integral from 0 to some final energy of dE, and this is going to be equal to the amount of the integral of dq over, q times dq. The capacitance is a constant. I can bring that outside, so this is 0 to the final charge. So I'm going to get the final energy, which I'll just call E. Don't worry about the subscript. It's going to be 1 over C, and the integral is going to give me 1/2 q squared, right? So it's going to be 1/2 q squared. So I can put the energy stored in the capacitor in terms of the charge and the capacitance. If I know how much charge is on the plate and how much the capacitance is, I can figure out the energy. But I can put this in terms of the field, because capacitance, if we go back to the definition here, capacitance is Q over delta V. For a parallel plate capacitor, we know that the electric field inside the capacitor is the charge per unit area times the constant epsilon 0. Okay. So I can say that Q then is going to be epsilon 0 times the area times the electric field inside the capacitor. So I could plug that in. And then knowing that, the capacitance is going to be that charge, which is epsilon 0 A times the electric field, divided by the potential difference. And the potential difference is just going to be the electric field times the distance S, called the separation S here. The electric field cancels out, and then the capacitance just depends on the dimensions of the capacitor and this constant. So let's plug all that in. We have then the energy stored being equal to 1 over the capacitance, so that's epsilon 0 area, and then we have S up here. We have a factor of 1/2, and we have the charge in terms of the electric field, so that's epsilon 0 A times the electric field squared. So what am I going to get? I have epsilon 0 squared, I have A squared, and I have the electric field squared. That cancels out a factor of epsilon 0. That cancels out a factor of A. So those squares go away. I have 1/2 electric field, 1/2 epsilon 0 times the electric field squared times, I have a factor of S left over and a factor of A. So that tells me the amount of energy stored in the capacitor is proportional to the electric field, the magnitude of electric field squared. So it's suggestive that there's energy stored actually in the fields themselves. Okay? And now we derive this for a capacitor, but it turns out, what's S times A? The distance between the plates times the area of the plates is going to give you what? The volume, right? The volume of the space inside the capacitor. Okay? So this is 1/2 epsilon 0 electric field squared times the volume. And if I say the energy over the volume, just divide through by the volume, I get 1/2 epsilon 0 E squared. This turns out to be a general formula. And this is the energy density for an electric field. Energy density meaning energy per unit volume. So this is for electric fields. It's true for any electric field, even though we had derived it for this specific case of a charging capacitor. Doesn't matter if it's uniform, non-uniform, radiative, whatever. That's energy density for an electric field. Turns out there's energy stored in magnetic fields as well. I won't go through the derivation, but the formula looks similar. It turns out that for magnetic fields, that the energy per unit volume, or the energy density, is 1 over 2 times mu naught b squared. Okay? So the energy density for both of these cases turns out to be proportional to the square of the magnitude of the field. Okay? So I could write the total. I could say that in general, energy density in general is equal to 1/2 epsilon 0 times E squared plus 1 over 2 mu naught times B squared. Okay? So if we have an electric field, any electric field, we have energy stored that we could make use of. Okay? If we have radiation, we already know some relations between the electric field and the magnetic field in radiation. So in radiation, we know that B radiative is equal to the radiative electric field divided by C. So that's true for any electromagnetic wave or pulse. So I plug that in. I have 1/2 epsilon 0 E squared plus 1 over 2 mu naught. And we have E squared over C squared. But if you remember, we worked out that the speed of light, c, is equal to 1 over square root of mu naught times epsilon naught. Okay, we saw that when we first introduced radiation. And so if I plug that in, I have 1/2 epsilon 0 E squared plus 1 over 2 mu naught. 1 over c squared is going to give me mu naught times epsilon naught, and I have another factor of E squared here. And the mu naught cancels out. And so I have 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared. And so this works out to be just epsilon naught times E radiative squared. Okay, so this is for radiation only, but it works out to be a simpler formula from the relationship between the electric and magnetic fields and radiation. Okay, so it's just telling us again that energy is stored in radiation, and it's proportional to the square of the magnitude of the field. So let's just try a quick question just using this. So let's say we have a pulse of radiation, kind of like what the first thing we saw when we introduced radiation, where we had this slab of field, electric field pointing upward, magnetic field pointing out towards us. And let's say we've confined it to just a box or a volume that's propagating to the right at the speed of light. And the height of the box is 2 meters, the width of the box is 0.8 meters, and the depth here is 0.5 meters. And everywhere in there we have a uniform electric field pointing upward of 720 volts per meter and some magnetic field, which you may or may not need to know. So we have the volume, the dimensions of the box. How much energy is stored? What's the total energy stored in the electromagnetic fields inside that box? So you can work that out. So what do we got? Okay, number of different responses. Okay, so what are we given? We're given the magnitude of the field, right, which is 720 volts per meter. Okay, and that's all we need because this is radiation. We could calculate the magnitude of the magnetic field if we wanted to, but just to get the energy density, all we need is the square of the radiative field, and I hope the answer's up there. Let's find out. The electric field is 720 volts per meter. Okay, what's epsilon 0? 8.85 times 10 to the negative 12. Okay. So if I say 8.85 times 10 to the minus 12 times 720 volts per meter squared. What's that number? What's that give me? Someone work it out. 4.58 times 10 to the minus 6. And what is this? What are the units? Is this energy? This is energy density. So this is joules per meter cubed. Yeah, joules per cubic meter. Okay. So to get the total energy, what do I have to do? Multiply it by the volume. Okay, and the volume, so the energy is going to be 4.58 times 10 to the minus 6 joules per meter cubed. And what's the dimension of the thing? It's 2 by 0.8 by 0.5. 2 meters by 0.8 by 0.5. So, well, 0.5 times 2 is going to give you 1, so the whole thing is going to be 0.8 meters cubed, right? And so this times 0.8 gives you what? 3.67 times 10 to the minus 6, which is up there, I hope? Yeah, answer number 3, okay? So 3 is correct. So this is energy density, not energy. Yes, question? No, because this is radiation, right? Okay, so we're looking at the total energy stored in the electric and the magnetic fields. Okay, so what we worked out here was you have 1/2 epsilon 0 E squared for the electric field, and you have 1 over 2 mu naught B squared for the magnetic field. Okay, but because it's radiation, I'm substituting in the relationship I know has to be true for electromagnetic radiation, namely that B is equal to E over C. And then when you plug that in, you get 1/2 epsilon naught E squared plus another 1/2 epsilon naught E squared, which gives you epsilon naught E squared. Okay, make sense? So watch the question. It's not just the electric field, but the total energy stored in both the electric and magnetic fields. Okay. Questions here? Just manipulation of a formula, really, nothing more than that. The key point here is that the energy is stored in the fields and that it's proportional to the magnitude of the field squared. Okay. And another way we can think about that is, okay, so once again, coming back to our demo, we had the electric field from the radio transmitter causing these charges, the mobile charges inside the wires to oscillate, right? So we can say that the radiative fields are doing work on the charges. So we can look at how much work is done. We can say that, let's say I have a, let's see, how do we want to do this? Let's say we have some electric field, radiative electric field coming in. Here's my electric field. Radiative electric field. And it is propagating in to the right, let's say. So again, speed of light is that way. Speed is that way. And let's say we have a charge here. Let's make it a positive charge just to make it easy on ourselves, like a proton or something. And as this electric field comes in, eventually we're going to have a positive charge in the presence of an electric field upward. So what's going to happen to the positive charge? It's going to move, right? Because there is a electric force. There's a force acting on it, right? And the force is equal to QE. Okay? So I can say, all right, well, the force is equal to Q times E, and it acts for some amount of time. So I can say that this pulse, again, has some width to it, just like our box over there. And so when this comes in, this electric field acts for a certain amount of time while the pulse travels through, and we'll call that time delta t. Okay? So we can figure out a change in momentum. We can say that just using momentum principle or impulse momentum theorem, however you want to say it, is that again, just looking at the y component here, delta p sub y is going to be that force times delta t, or Q times E times delta t. Okay? The pulse width, it lasts for a time delta t, but I could put that in terms of the pulse width, which is delta x, and so that delta t is going to be delta x over c, but neither here nor there. Then we can say, okay, what about the energy? So the final momentum, if it starts from rest, P final is going to be Q times E times delta x over c. The energy, well, it's going to require some kinetic energy too, and I could relate that to either 1/2 mv squared, or I could also say P squared over 2m. And if I square the momentum, I'm going to get Q squared E squared delta x squared over c squared over 2m. The constants don't really matter that much. What's important here is, again, showing that we get this factor of E squared in the energy, which is exactly what we got for the energy density, right? So there's energy stored in the fields proportional to E squared, and when it interacts with a charge, that energy goes into the charge. And so, again, the amount of work done, the kinetic energy that's picked up, has got to be proportional to that E squared once again, okay? So energy stored in fields, which might not be terribly surprising.